Alright, so we are going to get into Chapter 9, which is on acid-base chemistry. And first thing we're going to look at in Section 9.1 is on our definitions of acids and bases. Right. So, our oldest that we deal with, and this still works for us a lot of times, is called the Arrhenius definition. By the Arrhenius definition of acids and bases, we say that an acid is something that breaks apart in water to give us H plus and some sort of anion. Alright, I did this with HCl, but we could just make this a generic HA breaks apart to H plus A minus. Alright, that's an acid. Then also, by the Arrhenius definition, a base is, so I'm going to use sodium hydroxide as an example. That's our stereotypical Arrhenius base, but really it can be anything. Key with Arrhenius base is this OH, or this hydroxide ion, because this is going to break apart and give us Na plus and OH minus. Or, yeah, that's how that works. Now, or we could genericize this to just say that a base dissociates, it breaks apart in water to give an OH minus ion. Now, when we react an Arrhenius acid and an Arrhenius base, so let's react HCl and NaOH, those react to form a salt, okay? The sodium from here, chloride from here, and water. Water is always the product of an Arrhenius acid-base neutralization reaction. Now, we know, though, that there are substances that behave like acids and bases, but don't necessarily fit nicely into this definition. So there's this more expansive definition of acids and bases that we talk about called the Bronsted-Lowry definition. Okay, Bronsted-Lowry definition. Now, let's backtrack a little bit and talk about some things and kind of lay some framework for the terminology that we use in this. All right? So, if we look at an H plus ion, right? First of all, let's backtrack and let's talk about what a hydrogen atom looks like. Hydrogen atom is one proton surrounded by an electron. So when we make an H plus ion, this electron goes away, and that just leaves us with a proton. So we use H plus and proton interchangeably. H plus and proton we use interchangeably. We use that term a whole lot when we talk about acid-base chemistry. We refer to H pluses as protons, so remember that. Right? Now, we give the definition of a Bronsted-Lowry acid and base as, we say that an acid is a proton donor and a base is a proton acceptor. Alright, so base is a proton acceptor. Now, what do we mean by that? Alright, so let's look at our stereotypical Arrhenius acid again, but let's put it in the framework of a Bronsted-Lowry acid. Let's say we're going to dissolve this in water. Now, what happens to this, and the way we're going to frame it in Bronsted-Lowry terms, is we're actually going to get this H plus is going to go together with the water and give us H3O plus, and then we're going to get Cl minus. Now, this is just kind of reframing things, but it gets us more or less to the same result. By the way, when we talk about pH calculations, we'll come back to that, but H plus and H3O plus are, we can effectively treat them in aqueous solutions or solutions in water as being one and the same. Now, let's look at a Bronsted-Lowry base, though. And let's look at something like ammonia. Let's dissolve ammonia in water. Use these double-ended equilibrium arrows. Actually, I shouldn't have used those up there. That should just be a single-ended arrow. We're going to get NH4 plus OH minus. All right, let's analyze both of these, though, within the framework of this definition. Our HCl has acted as an acid. It has donated a proton to H2O for it to become H3O plus. So, within this framework, H2O has acted as a base. Now, as a result of that, after this interaction happens, we actually call this our conjugate acid. This is our conjugate base. Our conjugate acid is the thing that has accepted the proton. Our conjugate base is the thing that has given up what's left after we've given up the proton. Within this framework, ammonia has gone from NH3 to NH4 plus to the ammonium ion. This has acted as a base because to get to this conjugate acid, it has accepted a proton. Now, in this case, water has acted as an acid. Okay. And then our OH minus here is our conjugate base. All right. Base, acid, conjugate base. Now, notice here, water is a base. Up here, water is an acid. So, is water an acid or a base? The answer is both. Okay. Now, that also leads us to something called the autoionization of water, where we can actually take two water molecules, and this happens to a very, very small degree. We'll talk about that when we get into doing pH calculations, but a small amount of water actually does break down into H3O plus and OH minus. That's called the autoionization of water. Right, and that covers kind of the framework of section 9.1.